Recording is on. Good. I share my screen. Okay. Second week. Well, first, okay, this is Aula Web, my view of Aula Web. And you see that I've uploaded a basic shell commands. Basic shell commands is, oh, sorry, okay. Basic shell commands is just a few notes on the most useful, from my point of view, most useful shell commands, and I will update this this file, just a sort of scratch pad, just to have ideas. And there is also exercise in the classroom we will use today. I point out your attention in that the study material for this week is here. No, sorry. No, this was the video. The study material. Okay, the previous week. I have uploaded an updated version of the slides. I've made some small corrections. I've updated something. Instead of writing and substituting the original document, I've uploaded a new version. Anytime I will do that, I will upload the new version, because I don't know if some of you is using the tool for making notes on the PDF files on our web, and unfortunately, if someone uses that, this is called Alma Note or something like that. If you do that and I change the file, or notes are lost. So we have to upload a new version every time. So today I will comment this second version, the new version, I mean. Let me change and go directly to the not here. Where is? Okay. Well, can you see the slide? You see? Do you see?
Not the slide.
Okay. Okay.
Yes, Professor.
Okay, I understand. Let's go on. So this is the classes. We are here. We are here. So the kernel, as this very moment, is composed by the.
Sorry.
Yeah.
I can't see the slide.
You can't see the slide.
Yes, we can only see the folder.
Ah, you see the folder. Sorry.
Yeah.
Sorry. Strange. Okay, maybe this. You see the slide?
Yes. Now.
Yes, now they are.
Yes.
Sorry. This, yes. It was my fault. So the operating system for today is composed by user processes. We know what they are, including services in the user space. The upper side is the kernel memory, the kernel space, and and the components we have discussed. So drivers, that are pieces of code managing directly peripherals, including the network, not depicted here. Interrupt handlers, and these are routines that are directly executed as soon as the specific interrupt excites calls the routine, and as soon as an hardware interrupt occurs, the running process is interrupted and the code is executed. System calls are similar to interrupt handlers, logically are the same, but they are called directly by direct calls by user. Upon return from interrupt handlers or a system call, the switcher is always operating, and the aim of the switcher is to select the new process. Remember the states of the processes: ready, waiting, or suspended or sleeping, and the switcher picks up one of the processes following the rules of the scheduling algorithm. Well, now we get inside the process. The process, theoretically, what is a process? But roughly speaking, the process is composed by 3 parts in memory. One is the text. The text is exactly the executable code. Every modern compiler, when I say modern, I say a compiler after the years 70s of the last century, generate separately executable code or instructions in a different area with respect to data. Older compilers used to mix them. Now they're completely separated. So aside the text, that is the executable, there are data, the private data of the process, and those special data that are used for both numerical data and return points from function upon returning from function. That is called the stack. All modern languages use the stack. So I assume that you know exactly what it is. So the 3 parts of a process. Each region has an independent address space, so they can be also scattered everywhere in the memory. This is a very important concept that has no special consequence for us as programmers, but we must be aware that the text can be shared by several processes. Shared since there's no need to have separate copies of the text when several different processes have the same body of instructions. It's not so important to have a look at this and to understand completely, but just consider this main and different parts that are composing the stack, data, and the text are evidentiated separately. These are variables that are pushed on the stack. This variable pushed on the stack, and also the return point of the function is pushed on the stack. Data are in the data part, and text is everything is in instructions. Skip this. I will erase in a successive editing of the slides. Just to have an idea, processes in Linux, Unix are hierarchical and are distinguished by a process ID, PID, we will see after. So just to have a glance, a picture, just to remember. The aim of each process is to generate new process, forming in this way a tree. So processes are distributed in a tree of processes. And the tree has a root, and the root in an operating system like Unix, Linux, also in Windows and in OS X. The root is always a process whose number is 1. The number 1 is the process ID 1, and traditionally in Unix Linux is called init, because it's run, we will see after. So far, we can depict processes with the different components of the processes. We have here, we don't know what is here in the pink part, but it's very important, and we will discuss, is the way in which processes have communication each other, the basic communication between processes. And the pink or purple, I don't know which is exactly the color you are seeing now, this part is here in that table. So data structures are, the question is, how many data structures are managed by the operating system, are needed by the operating system for managing all processes? Go back just one step. So which data structure to put here? We aside.
Professor,
Yes?
we cannot hear you properly. Yes.
I can't understand. Speak slow.
There are a few disturbances.
Too loud. Repeat, please.
We cannot hear you, Professor.
You cannot.
Yeah, you are not audible. There are a few disturbances.
You're speaking too close to the mic, so I can't understand exactly what you say. Speak.
Professor, you're falling off. We're not able to hear you.
I'm falling off the screen.
No. As in mic, in terms of mic, we're not able to hear you
connection.
sometimes. Yeah.
The connection.
Yeah, seems your connection is a bit unstable. Now it seems better, but before there were a few seconds where everything froze.
Okay.
But now seems clear.
I had an alert with the connection, the poor connection, but I'm using the cable and the university connection, so it should be a perfect one, more than 100 kilobits per second. So I don't know, maybe something. Now, is it stable?
Yeah, it seems
Now
like
it seems to be stable, yeah.
Yes,
stable, yes.
Was this a temporary fault due to the infrastructure? Because I'm just at university and not at home, just to have a good bandwidth. So I was saying, the question is, we want to keep on putting things here in the resident part of the kernel space. Drivers, enter handlers, system call handlers, and the switcher, so the scheduler. But which are the other components? There is one other big component, just one other component, that is the set of data structures to so that the kernel of the operating system know each process, the needs of each process, and the parameters of each process. So everything about the process, where it stays, in which part of memory, which are the input-output channels open, a lot of things. So it's the last component we want to put here in the upper part of the drawing. And so the question is, which are the data structures that the kernel uses for process management? The process table. The answer is the process table. It's a big table composed by several subtables linked using pointers. So we will see just the main components, just to have a general and rough idea. The process table is always resident, so never swap it out of memory to the disk. It is part of permanent of the kernel. and contains an entry for each process. The entry is just the memory address, the code address, and so on, the entry. And so also everything is called the context of a process. So all the information needed to run the process. The purple or the pink part that I here upper is the so-called user area. Here is written that it is not necessarily resident, and that's true. That's true. Can be loaded into memory of the kernel when the process runs. Otherwise, can be swapped. In modern, present machines, usually it doesn't happen. So to make the system faster is resident as well. But logically, it's possible to swap out. And it contains information necessary to the kernel for the management of the process. And basic information is which are the files, the open files. And we will see that open files are also the way of making process communicate each other, so inter-process communication and even network communication. So the concept of file, we will see in POSIX, is an abstract concept. It's simply a channel, a communication channel. So don't think of a file as a hard disk file. Is a communication serial channel. Signal masks, we will see what is a signal mask, really important. How a process reacts upon receiving an interruption, a software interruption, typically what we have called signal. And some accessory information for accounting, the computing times that are used also by the scheduler, since it must compute how much the process is running, so it will decrease the priority and so on. And so the kernel needs the process table, which is a map of all processes for each process in the user area, and the queue of ready processes. I have an alert, my internet connection is unstable. Is it true? Or you can hear me and see?
It froze some seconds ago for like 5-6 seconds. Now it seems better.
Okay.
But when it freezes, we can hear what you're saying.
I have also a Wi-Fi connection. I will to avoid conflicts. Okay, we go on. So shortly in two pictures, just just a very rough picture with a long list of all information regarding. Consider the process table as a vector with many entries, one for each process, with many pointers. For example, a pointer to the page table. The page table is simply all the memory pages, so the memory segments that are used by the process. We will not go back into this concept that is a concept related to the structure of an operating system of the memory management. But so the memory map used by the process, the identity of the process, the parent process, because we have seen that processes are in a hierarchy, so a process runs children processes, so there is a parent. The owner of the process group, not written here. The process state, the scheduling state, is waiting, ready, running. Resident, maybe resident or not, scheduling parameters and so on, dimension, everything. We go on, and the user data. So you see other elements. You don't have to remember all these concepts. I want just to show general concepts. So please don't consider mandatory to remember exactly all the lines of these slides, just the general concepts. So a process as a user area. Note that there is a text table, there is a subtable, there is a table that, so a vector pointing to all texts, since a text, so executable code, can be shared by several processes and executed separately by several processes, there is one dotted line, so another user area can point the text table with the same text. So this is the other components. The total description or total store of all elements, they are defining what is called the execution context. So everything is needed to pick up a process from the ready queue and make it run, because immediately it finds where is the stack, where are the data of the process, where is the text, and all other information stored on the system process table for that process. Lastly, there is the ready queue. The ready queue is managed directly by the switcher, and the switcher has a queue with a list of priorities, and where the process that is picked up to run as a pointer to all data describing the process itself. So we have concluded the drawings. This is the kernel. So you see that in principle, a simple but true kernel, a real kernel, is not composed of many components, just managing interrupts, so the interface, the physical interface with the electronics, a set of system calls, so services directly executed in kernel space upon request by the processes, and they are, and I told you, are similar in logics, since in any case the running process is interrupted, then the switcher talks and decides what to do. The switcher has a look at the ready queue, and the ready queue there is a pointer to the process table with the process that is selected. You see, the process table is much bigger than this, and this is the selected process, and well, this is one of those processes selected, and there is a pointer to the process itself. So in principle, there are not many components to take into account to understand how it works. So this is the sort of background that we must have to understand exactly all the system calls we will describe later. Okay? Memory management, we can skip for now. We will go back in the end, it's not important. Swap with, okay. Memory in general is managed in a special way, since the concept of virtual memory was established by IBM in the years 70s of the last century, and from that point history, all systems are similar, so that each process thinks to have the availability of the whole memory, not only the physical memory installed on the PC, on the computer, but the virtual memory whose extent is decided by the addressing capability. If you have a 32 bits microprocessor, now every processor is a 64 bit, but 32 bits, since for 32 bits I remember the number. you can, if you have a 32-bit, you can address 4 billions of memory addresses, even if you don't have 4 billions of memory addresses physically. And this is the first concept in virtual memory. The second concept is that even if you have n running processes, each process can use virtually for billions of addresses separately from any other processes. This is the concept of virtual. You may have 100 processes, and in that case, you have 100 times 4 billions memory locations. You don't have physically, so the hard disk, secondary memory, is used to manage copies of that. That's the idea. So memory is continuously swapped out and swapped in. Not in robotics, usually. So it's an important concept because if you want a real-time system, in general, you need to stop or the swapping system. You want that all your processes reside always in memory, because if you have a real-time specification, you need not to wait in the execution. You need a fast execution, and swapping in and out make the system in general slow, 10 or 100 times with respect to direct execution. So it's in any case, it's a concept, is a topic that you must take into account, even if a good robotic programmer usually forbids the system to swap. So, shall we rest for 4 minutes? Okay?
Okay,
Yeah, 4 minutes pause.
thank you.
I resume. Sorry, the recording was off. Unix processes. In Unix, and in general today in every kernel, a process, no process exists without having been created by another process called the father or the parent of that process. So we have seen that processes are in a hierarchy. A hierarchy is a tree, there is a root, and the root is the only process by convention. Its identity may be 0. Oh, this is a mistake. It's not 0, it's 1 in Unix. So I will upload the updated file. 1 who has no father, and so it can be created only by the kernel at boot time. When the system starts, this process is created. Otherwise, there's no other possibility. From now on, all processes are created by processors. And each process, as soon as it is created, the primitive for creating a process is called fork. I don't know why fork, but yes, graphically it's a fork, since there is a process and 2 descendants. A process runs until it decides to exit, and this is done by a special system call, just like fork. From now on, everything we say is related to some system call, or maybe is directly killed by the kernel itself. We will see which are the reasons of killing a process. So either a process decides spontaneously to cease to live, or the kernel, after something happened, an event, a signal in general, decides to kill the process. So the process is created by, this is the first system call. We see it now very briefly. We will see exactly what the syntax and all the examples on how to use this. This is called fork. PIDT is one of the system types that are available in the C language interface. PIDT, all system types have these structures with underscore T. In any case, it's int. Absolutely equivalent to int, and can be mixed freely with int. So no parameters, and fork creates a child process. Well, child process is a bit misleading, since the idea is that the process generates a child that is identical. So it's a sort of clone. So the reason why it's not called clone probably will be clear after. In any case, the child is absolutely identical to the father. Absolutely, there's no difference at all. The only difference is in the return value of the fork, of the fork. Because this has to be clarified. Since in this moment, at the moment in which the process asks the kernel to execute the system called fork, immediately a new copy of the same process appears that is absolutely identical. So the new copy includes also the fork call, the code of the fork call. So both father and child think to have executed the fork. The only difference is that the father has a return value that is the process ID of the child. The son or the child has a return value, since it thinks to have executed the fork, and a return value conventional 0. 0 cannot be process ID, and so the child understands that it is a child and not the father. It's the only difference, and is an external difference. So it's not in the what is laying in the memory. They are completely identical. Each system call, we will see after, also return a negative value if an error occurred. Process 0, okay, another, I will correct. Process 1. This is an example, very simple example. P, that is the int P, or process ID type, int P, equal fork. So fork is executed, the return value is assigned to P. If P less than 0, the fork failed. So you must do something, and we will see what to do, because it's it's an exceptional case, but must be treated in any case, in robotics in particular. Else, if P is equal to 0, here the code execute that you want the son executes. Else, the code for the father. but both codes must be in the same file. In Unix, there is no system call to create a process that runs the executable X. We can do this, but with a special system call. So this is a picture that shows what happens when the father issues the fork. This time, this copy of the father is generated. It's absolutely identical, and this is the as the return value equal to 0. So this process knows that is a second copy. Let me call second copy. The first copy for the father knows that he is the father by the value, and this is a replica. It's completely identical. Note that here there is no text, but surely you remember that texts are shared. So the text in no case it is copied. Here the text, so the executable code is the same, shared with the other process. And the process table is enriched by a new process that is, in any case, a new process. This is the hierarchy we have already seen. And this is the comment on what the fork does, and we have seen that. Remark. There is also a system called clone, which is not POSIX. It's not POSIX, and in general is deprecated or discouraged. It's similar to, in a sense, it does what the name clone suggests. So generates a new process, but the only difference is that it does not duplicate the stack. So it does not duplicate the stack, nor the code, of course, the text. But the fact is, the stack is not duplicated, implies the fact that you can hardly run two separate processes sharing the same stack, because you must distinguish you must separate the stacks to push into the stacks data for functions, for areas of code, and so on and so forth. So it is possible to use this in some cases, but in any case, you're discouraged to do that. So we will not get into this. After you have issued the fork, you can call the system call exec, that is similar to the fork, but replaces the image of the caller with the yes. Are you asking something? No. And this is with the definition of fork that I gave you. The two processes have identical code, so you must distinguish the two algorithms using the if you are the father, if you are the son, but the code inside is equal. There is also the possibility of substituting the code, so sending into execution a real new process. We will see when we do this and what is it for. So this is the picture so far. in that case, the exec operates exactly in the same way, but in that case, it duplicates gives the new process a new text. So that's simply the difference. In that case, you have seen that there's no code, the executable code, because the original code is shared and executed by both processes. The exec has the same execution meaning from the point of view of the operating system as the fork, but generate a new text. We will see how to use. Exit terminates the process and so on. Oh, we don't know. Another important primitive is the very, very useful is a primitive, a system call to wait for a termination of some process. Typically, a father process or a parent process can wait until all its children are terminated and is able. So in that case, this recalls the idea of the father process as the monitor of the family of processes waiting for the termination. Wait means that is aware of termination. It's not necessary to do something particular, but wait is just to be intended as the child exited or not. So it's a sort of poll on the status of a process. And status is a value that a process can give back to the father, just like a return value of a function. These are examples, so we go on. A zombie and orphans, this is a detail, so we skip, we will see after. Just the detail, not interesting here. So forget for a while the idea of zombie. Zombie is just a process that decides to exit and is the status, temporary status, just after exiting and before the kernel erases it from the process table. So it's a temporary status. But sometimes if you have a look on the table of running processes, you will find a process in the kernel that is flagged with Z. It means that the process exited, but waiting for the reset of the process table. Idle is a temporary state, is a process that is just after fork, a new process that is by definition ready. And so also this status is a temporary status that becomes ready after a few milliseconds. At boot. Some of you has a microphone open, please close the mic. So the system initialization, we can see, so the logics on when you boot a system without a graphical interface or a graphical interface just after this process. So in the first phase, the bootstrap just runs the first process, the process 1, not 0, also in this case. The process 1 that's called in the Unix, Linux. Please, there is a lady with the microphone open. Please close the microphone. Well, when you hear that, close the microphone. The process number 1 is always running and will run forever. I cannot see which is the one with the microphone open.
Sir, I think you can mute everyone here because you're the host.
Yes, I can do, but I have to share for a while. I have two participants. It's strange, but I can't find someone with the microphone open. That's strange.
We can see here, sir, with the microphone on.
I have the microphone on, but no. Dominic, this one, maybe you.
Yes, yes.
Okay, I've muted. No one else. Okay. So the process number one, during boot time, forks several times and makes successively fork and exec, the one that I just skipped, but the meaning is that execute the new program. These programs called getty are programs, system daemons connected to the possible users, and the procedure for log on or login in the system. There may be several. In general, a multi-user system has several lines for that. There are terminals or virtual terminals in the network. And so after one of the users, for example, the first one, logs in, a new exec runs the famous shell. The shell stops and waits because it's the interface, the textual interface. So you see that there are no different, the concepts are very few, and we use them, and we will use the shell just to show a process already written with all the characteristics of any other process, including capability of forking, executing new processes, and so on. So the login, the shell is nothing but a point in the hierarchy in which the higher level has executed new processes. And obviously there are processes, not services in general, they're called daemons, not in Italian, daemons. There are services for system-wide purpose, so they are not connected to single user. So this is exactly what happens in the operating system. The operating system is just a series of processes that fork and exec until everything is calm and you have just shells and other system daemons running. Okay, so for example, the shell structure, if you have seen the video introducing the shell, the user interface, sorry, if you have a graphical subsystem, for example, the Linux that I'm using now in this moment has an X window server. So some of them has run the server, and the server gave me a graphical interface to run commands, just pointing and clicking, but nothing different from this structure. Is just one of the services permanently running due to the successive fork and exec of the of the init. So what is the shell? The shell is waiting for commands. You can set a command like that, the name of the executable file with arguments, and it executes. Or you can write this with the ampersand and execute it in background. What does it mean? We will see. Because we will see not to know completely the shell, but because there is a concept that is important for us in running processes and writing concurrent programs. So aside the background execution, the shell structure is very, very simple. It's an endless loop, right? Here is a loop with the loop is not present here, but write is another system call that we will learn very soon. It is a general way of writing or reading something through the abstract concept of file that I've mentioned. The file that in POSIX is a serial channel. Number one, we will see, is the standard output connected to the interface we are using now. Prompt is simply a character or a string that says something that to me, saying I'm waiting for a command. So this is a loop for just one string, and is cryptic, but you see in a cryptic C that simply reads a string of 80 characters. Here is written that parses the file name and the arguments, and then forks. Simply, the shell itself forks for executing the argument. If, let me share another. Okay. This is a shell. The prompt that I've mentioned is this one, very long. Usually the prompt is conventionally is the path name of the working directory in which you are, just to avoid errors. In this case, the path name is very long because it's a USB key. This is mounted in some place. So the current directory is called 3week, the subdirectory of this one, and so forth. So I'm here. The shell simply, we can see here, is, so this is the first line. The second line, input a line and parse the file name and argument. For example, ls minus L. ls is a file name. File name not necessarily has to be in the current directory. This is a file name in a standard system directory, and the shell is able to find it and execute. Minus L even is a strange argument, but the shell conventional way of having so-called switches or parameters is this minus and literals or text operators. So this is the second line. And immediately after, the shell forks and executes the file ls. The execution of the file ls is just to list the directory, and then the shell goes back to the right and wait for prompt. So it's very simple. This is a clear example. I will show you just a few minutes later another what is the concept of background. Stop share and share again the inter-process communication.
Professor?
So after we have until few slides, and we will rest after 3 slides, I think. Well, so now we know the concept of process and the initial ideas on how to run a new process. So we have an idea that processes are composed by data, code, text, the stack, and the user area with information that we will be you will be able to use because are really important in the communication between processes, and also the ability of running a completely new process by simply substituting the executable code of the father process with a new executable code. So we know that there are the possibilities of running processes or inter-process communication. Now we have to talk about how they communicate. In the very first slide, when you mentioned the communication mechanisms for a concurrent program, you mentioned several ways: push, pull, send and receive data, blackboard, and so on. POSIX, these are the basics of POSIX. We will see separately the concept of blackboard, so shared memory. But in this case, direct communication is based on a send-receive paradigm. The two methods for making processes communicated are pipe and socket. But both the pipe and socket, they are the first one we will learn probably starting from next week, I don't remember, are not new concepts. They are simply special input-output in the sense that they use the concept of file, and the concept of file is just a serial channel for communication. So we spent some words about a concept that is completely different, that is the event mechanism or event principle. So a communication that does not carry or communicate data, but only the fact that something is happening in this moment. The concept is the abstraction of the interruption, of the interrupt, the hardware interrupt. Some hardware interrupt generate directly these signals, are software interrupt, but most part of signals are raised directly by processes. What is a signal? A signal notification, a notification that something has occurred. So signals are completely asynchronous. That's the important concept, asynchronous. So may happen anytime. You cannot foresee when you write an algorithm when a signal will be raised and have effect on your process. Some simple elementary situations are floating point errors or numerical errors in general, and also the death of a child, unknown death of a child. Or one process that requests one process to terminate, even if the process had no idea of that. He had an algorithm to carry out. Is typical. You remember the first example that will be developed of the mobile robot that I want you to develop, you continue to develop, because you will, we will use in writing software for this. Termination, for example, an emergency situation or a red button emergency, stop everything. Signals are software interrupts and can be sent by one process to another process, by a process to itself. Not so common, but can do, and in many situations from the kernel to a process. Each signal is identified by an integer number. So signals have names, but all the Unix kernel uses the simplest way of giving names. So processes have integer numbers as names. Users have integer numbers as names, and signals. We will see that also file, as to say, channels have integer numbers as names, and signals as names. Here is a list of the most popular signals. In a header file in POSIX, there is also a symbolic name that often used, but is simply a macro that defines a value for this. And you see that these are signals that can be raised and can be received by any process. They are distinguished by value. The famous 9 sig kill, that is the name, recalls the fact that it used to terminate a process abruptly. There are many things that with an associated action. We will see that the idea, really important, is that there is a default action. So this is the effect. In most cases, the process that receives a signal terminates. In most cases. In some other cases, terminates with logging the memory image of the process. So this is in any case termination, but not only the process terminates, but a file is generated with the memory image of the process just for debugging purposes. So you see that almost, we will see what is stop. Stop is a scheduling action. Stop means that the process from running becomes waiting. So this is, in this case, they can be, they do not exit, and this scheduling can be resumed by another signal, that is continuation signal. So a process that is in waiting state becomes again ready, not necessarily running. Is ignored, but very rare. In most cases, the default action is termination. Why is termination? For safety reason. So the safest or safe status of a process is the dead process. So in any case, in case you receive, you die, you process, I mean. But another idea is that here is, we will see the system call to send a signal. that is called kill. That is a strange name because it doesn't kill. Should be send signal or something like that. But the name, historical name is kill. But this name is misleading. It's simply send a certain event, a signal, to the process whose name is PID. But the important, very important thing is that you can write how to manage a signal upon reception. So if you don't say what to do, and there is a system call to do that, see action, you describe when you receive signal number 7, what to do, you write here. If you don't write, probably your process will be terminated. Otherwise, you write, and this is called the signal handler. Going back many slides, I want to simply point out that this is one, okay. So in a sense, you write here in your process an interrupt handler, the code for an interrupt handler. You write it in the user space, not in the kernel space, but logically is exactly the same interrupt handler does. Interrupt handler executes code upon reception of a hardware signal. In this case, you write a code to be executed upon reception of a software interrupt. Logically, they are very similar, but the main difference is that you own your signal handler in user space, so it's not inside the kernel. This is the idea. So you can write what is called a signal handler, or you can simply let the default function to be carried out. But you can also mask a signal. Mask a signal is similar to writing a signal handler that does nothing, but there are very small differences. In that case, you block the signal. You are completely, you don't, you close your eyes if you don't receive the signal. And is faster and simpler than with respect to write a proper dumb signal handler. Some examples for the shell. Control-C and Control-Z by the driver of the keyboard generate signals. So they're not hardware interrupt. They are signals generated by the kernel, the device driver of the keyboard. The Control-C is most common. Just terminates the process. Control-Z stop the process. We will see. And in some cases, the process can start again. So Control-C is not the magic key in the keyboard. It's just a way of sending a signal. We will see an example in which we can also write a different signal handler for the Control-C, preventing the process to stop. Signals can be received only by process of the same owner, or for security reasons, of course, you cannot kill or kill in the sense that send a signal to a process that you don't own, but the kernel can send signals to everybody. Signals are managed by additional information on the process table and the user area. In the process table, there is a vector with all a bit vector with a possible signal. So a signal, when a signal has effect on a process, just put to one, writes one on that, on the slot of on the position related to that signal. And in the user area, there are pointers to the signal handlers, of course, because you write your signal handlers. And also signal mask is not written here, but there are also signal mask in the user area. I must add signal mask, that means which are the allowed signals. By default, all signals are allowed to be received, and but you can specify that some signals are masked. Signals are not enqueued. They act exactly like other interrupts. So if you have a signal, a pending signal that is next to be served, a successive signal is ignored, because, or if it's fast, it rewrites the previous one. They are not in queue, like interrupt, like other interrupts, because they are, the idea is that signals should be, and in general they are, executed very, very fast by a process. Okay, this is the pack of slides that concludes the, let me say, the well, a description, synthetic description of the kernel. I think I mentioned more or less all elements of a kernel. So you see that it's not much complicated. Even those of you who didn't follow an operating system course, I think they're all elements that you can learn, understand in principle, and they are very important to be the background on which to learn how to use the system calls. Okay, so we are again, we can there are questions on these topics. As I told you, this concludes the theoretical part. Let me say that is very, very rough in a sense, that I try to put the fundamentals of an operating systems in just a few slides and in a couple of weeks. There are some topics that should be also discussed. For example, the file system. We don't have time to do that. We will discuss also the abstract concept of file that POSIX uses, as to say, the communication channel. And other topics, but I think that it's good enough. So shall we rest for a few minutes or so, and then I will give you a strange task to solve in real time in groups, okay? 5 minutes, stop. Stop recording.
Professor? Question, please.
I resume the recording, okay?
The code that you showed with respect to the prompt, right? There was a variable called buffer, right?
The code that we have shown in these slides, you mean?
Yeah, in the slides with respect to prompt, and then there was a buffer, right? Is the buffer a variable that we provide, or is it just taken directly
well, the
from
buffer,
the computer?
the buffer.
Yeah.
Well, the buffer. Well, this code. This is the code executed by the shell. The shell execute. Okay. Let me go back. We will see a more detailed example, but the read 0 buffer 80. Well, buffer is supposed to be a char vector So there's no
Okay.
data definitions. This is an except of the code that is, from the point of view of programming, has many errors. Read is the function that asks to read from this 0, integer 0, is the name, standard name, we will see, of a channel of an abstract file that is the standard default input, so the keyboard. Reads 80 characters into a variable that is a char vector. And so this is a side effect of the system called read. And read gives back the number of characters read. And this is different of zeros. This is the so very synthetic code, but we will see also the right code because it's one of exercises. Okay.
Okay. Yeah. Thank you.
Good.
Sorry,
Yeah.
I have a question on the same slide. I have a question on the same slide.
Yeah. I understand. I have to find out the slide. Here is the slide.
Why fork return 0 for the child?
This is a definition. Definition of the fork. We will see also in well, the exercise I will ask you to do just after the pause is related to that. Fork, the definition of fork, the system called fork is that it gives you back a value. The value is 0 in the cloned or the copied or the new copy of the process, and the value is different from 0. In particular, is the process ID of the son in the father or the parent side of the process. That's the logic.
And why in the slide with the hierarchy, the father, the parent have 0?
I have to correct because it's an error. So there's no 0 process. Well, in this slide is an abstraction, is not the...
Not in another.
Okay.
I think it
this
was...
slide process 0 means the bootstrap that is before the process hierarchy. So to be coherent, and since it generates 1, is 0, but is an abstraction. In a previous slide, you mean here?
Yeah.
No, the process ID is 1. And this is the...
But the child?
No, the process, these are in this slide, we have the tree of processes. So the first number is the number or identity of the process itself. So the process ID is 1. The PPID in Linux jargon is the parent process ID. You see, in that case, the child of 1, these numbers are randomly chosen, so that we don't know. It depends on what time it happens, this fork. Since the names of the process IDs are unique in the system, the kernel guarantees that it is impossible that 2 processes have the same process ID. So when the fork is issued, the kernel, to execute the fork, finds the first free process ID. In that case, we suppose that process 1 has process ID 101, and the parent process ID is 1 because it's father. So this is just a drawing, so don't consider it very. The important thing is it's coherent and there are no errors. But okay.
Okay, thank you.
Okay. You will see the example now. But stop share, stop recording, pause recording. So we cannot record that, but I've given all the students the exercise that is in our web and divided the classroom into small groups and asked to all groups to understand the code and decide what is the output of the code. As soon as and we will discuss tomorrow the result of that. So I close the recording now.